So I hope you got a. Oh, it's not shown there. Why? Is it not on? It's weird. It's not there. Seems to be weird. Why computer one like this? Let me check. It's not on. What happened? Oh, it's on, but the color looks weird. Though. Anyone has any idea? It's not. It's not working. Why? Anyone any clue why it's not working? Oh, that's good. Something weird happened. I'm sorry about that. I think it's okay now. So I think we can start. For some reason, it was not working at the beginning. So let me quickly review what we have done in topic 3, because this is like 2 weeks ago. I hope you got a nice break of holiday. I mean, of course, we also have a public holiday this Friday. Hope you enjoy the hiking. So what we talked about in the 2 weeks ago is about solving equilibrium. I guess you have done your assignment, and then for the first 2 topics, and after today's class, I think we can release another assignment that contains equilibrium and uncertainty. For equilibrium, that's simply saying that how you would solve different model. And I would say this model you would be using most of the time, I would say, when you rewrite model, unless you're doing a very sophisticated type of model. And these are the model that actually you would use in your work, and you almost always find it in a lot of application in various paper, even though they look very simple. The reason is being that they are the baseline, the model you want to build, and then you want to add things there, right? Suppose you have a Carnot or Bertrand. That is most classical way to model firms' competition. And here we just focus on, it's very simple, right? Carnot just quantity, and the Bertrand is price competition. But you do allow, say, supply chain, then it's more complicated, right? Or you, in terms of, say, in accounting practice, right, you would have competition between a big audit firm, right? But also you also look at the financial market, right? The investor will invest, right? And that's why we often the time when they using accounting paper, they would assume that the competition in capital market is perfect competition, right? In that case, makes things easier, but they allow the accounting firm competing in Carnot or Bertrand style. That is how things work, or in marketing, right? They would allow, say, in the supply chain, different channel, right? They focus on one channel is following Conrad and some channel following Bertrand, right? Maybe the top tier, the niche market will be following Conrad, and the low quality goods is following Bertrand, right? These are the things that you will often see. And of course, you look at trade model, right? Supply chain paper, when you talk about different firms doing importer exporter, they would do monopolist competition, right? But of course, another chain, then different part of the chain can have different types of competition. But you can see, you can mix and match, right? For some of the paper I'm working on, I mean, I do innovation, right? Then I would focus, say, to make it easy, then I would focus on product markets, Conrad, and R&D market can be very complicated, right? So these are the way that you would combine different model and build up a very large model. It's like a Lego, right? Each small part is very simple, a wooden board, right? It's very simple. But when you combine different parts, then immediately it can be very complicated. Okay? So it's not something that we learn some easier model, then it's not going to apply, but easy model is good because no one would question whether your model is good because we know it. So often we use, then it's a technique that you would want to build. And same for all the model we talk in this class. It's very simple, right? But when you do research, simple is not bad, okay? I mean, I guess, at least for my stage, at your age, I would be thinking that, okay, I should find the most complicated model in the world and generalize it or make it more complicated. Then you will fly and publish in the top tier. Usually it's not the case. Usually what you do is actually the most simple model, and then you combine and suddenly a very interesting problem. And that would be more important than try to come up with the most complicated model and try to solve most general question you're asking. But you would, as a business school or applied paper, usually you focus on is finding out a right question, which would be meaningful. And then you try to figure out a model which everyone accept this type of model is the right way to model. And you put it there, and then you solve it, then it will be nice. Of course, cannot be too trivial, the answer, but when you combine different parts of a simple model, it can be easily go very complicated. Okay, later when we learn game theory, you will notice when the game have multiple stages, then already very complicated. Even each stage is very simple. It can easily go very complicated, especially with multiple equilibrium at different stage. I will make more clear when we go there very soon after today's class. I mean, uncertainty with the game theory, then you will notice easily model can go expand very quickly. Okay, so that's why we have to keep our core as simple as we can. So that's why we cover something very trivial. And perfect competition is okay. Don't feel bad when you have to use perfect competition. Don't feel bad when you use Bertrand. That's okay. As long as not the whole thing is Bertrand, not the whole thing is something simple, then it's fine. Okay. And of course, what you try to model must be not to be too far away from the reality, right? So, right, what I meant is, right, when you talk about Bertrand, right, you usually apply to the case where product are more or less homogeneous, then they compete in price, right? And that would be, you should fit in that way. Otherwise, people would question whether your result is driven by those modern assumptions. Okay? And now let me get to this topic, uncertainty. And some of you, if you studied uncertainty before, you notice that our treatment on uncertainty is really elementary. And of course, if you really want to do research on it, then probably you would have to go further. But what I do is just scratch the surface to let you know what kind of tools that you may apply to do uncertainty and up to the level that is appropriate for the graduate study. Okay. Of course, you can go way deeper than what I do here if you want to go to the frontier. But these are the things that that is rather standard. Okay. Now, if you look at the literature, there's many ways to model uncertainty. The way we do is focus on the classical one. That is really standard way. And then I don't want to deviate from this. But of course, the frontier is so much more complicated. The classical way we do is a classical probability approach. right? That where you know how you describe probability, right? You know what are possible outcomes, right? That are called sample space, right? You can assign probability. There's objective or subjective, whatever probability you can assign, and there's no question about the probability. Everyone would have the same idea. The decision maker exactly know what's probability of that event will occur, okay? And that is classical way you do probability, okay? So of course, in the modern research, this is not the only way. There are many ways to do it, but we focus on this very classical way. I mean, this is the same way you do in the undergrad. So I hope that will be okay. So look at textbook, or a textbook, we start with gamble or simple lottery, in the sense that you would describe the uncertain world by finite number of outcomes, okay? And we said finite because when you take infinity, then it can be very complicated, right? Those who learn probability in sigma algebra or the probability space, right? Borel algebra, right? Borel set, those kind of stuff, it can be much more complicated, right? But we focus on finite number of outcomes that make our proof will be much easier, right? Because at the end of the day, today we talk about expected utility, and we try to give the proof, very simple proof, that will rely on finite number of outcomes. If an infinite number of outcomes, the proof will be way beyond our scope, okay? The proof is very simple, don't worry. I mean, very similar to the way we proved existence of utility, if you still recall that, right? With the one bundle, right? What we do in the chapter 1 is to say the bundle, right? You can go to the left side, go to the minimum bundle, go to the upper side, the maximum bundle, right? Continuity implies there's some bundle on the 45-degree line, right? If you remember that proof, we will something related to that here. So let's start with n possible outcomes, and each outcome has probability pi, and then some of the probability is equal to 1, and the decision maker is facing this kind of gamble. Okay, an example like this, right? The red one, right? It's like this question is you can have probably 0.5 win $1, probably 0.5 lose $1, right? This rather standard notation. Okay, and but in the real world, right, it's more likely that the we face the world is more complicated. It's like the compound gamble, right? The idea is like it's a lottery over lottery, which means the following, right? Before we go to the terminology, maybe you go to the very simple example, then you just motivate what we're saying. Suppose you do the following: you toss a coin, whether it's a fair coin, then it's a head or tail. Then if you head, then actually you're winning. If you're tail, then you're losing, right? If you're winning, then say G1, right? If you win, you go to the G1. If you lose, you go to G2. G1 means you will win $1, $2, $3, $4 if likely. If you're tail, then you're losing. Then you will be losing the still it's losing $1, $2, $3, $4. Okay, so it just like depends on this, then you go there. Basically, you can draw a probability tree, right? You can draw a probability tree here like this. Let me quickly draw this one and then try to convince you this is. So it will be something like this. Is you have a G, you have a G1 or G2, right? So you have a, oh, it's not well, this one. So you 0.5. So I use the mouse. I hope you can still see what I'm writing, right? And you will say 1, 2, 3, 4, you're winning. Then, of course, the other 4 possibility, -1, -2, -3, -4, right? So that would be the compound lottery, okay? And that means a lottery over lottery. So that is the meaning of compound lottery. Well, the way you write is lottery, but itself is not outcome, but each is a lottery by itself, right? So that would be the idea we are talking, okay? And as I said, we want to focus on finite number of outcomes. If you want the treatment of infinite, then you have to look at the books, and there's some technical condition, but everything actually would extend. I mean, as long as you are likely willing to make some additional assumption, everything extend to infinite number of outcomes. Okay, and you look at book. When we find out number of outcome, then it's okay to fix the set of outcomes for A1 to AN. And some of the book would use the term, if they fix outcome, then they use lottery. Okay, some book would call gamble and lottery interchangeably. But for our exposition, then I will focus on the case when we gamble, then to get outcome. With lottery, I just have probability, because the outcome is fixed. What I need is just probability, right? When I say P, already implies the outcome is fixed already. Okay, and the set of lottery is the n-1 simplex, right? Because you add 1. And compound lottery, right? Again, it's the bunch of price, right? And then together the weights. Okay. So we don't need to write AI equal to AN because A is given. So capital A is given. Okay. So notation wise. This I think is also used in the book, so that's why I just use that. So if we fix the outcome is fixed outcome, right? Then I don't need to write P is the probability for each outcome that I'm done, right? I don't need to write 1, 6, 1, then just to save notation. Okay. And compound lottery over this, I just write the probability on each lottery, and each lottery just probability. Okay. So that would be half you get 1/6 for each one, but half only you get to this lottery is 1 up to 3. Okay. So that is a very simple notation here. Okay. Now, what we want to do now is the first thing probably is to try to understand the foundation of expected utility, which is the most common framework that we use in the literature, right? And you learn that in the undergrad, if you do the intermediate micro. And now we want to give you the foundation for this expected utility, right? And expected utility is if you look at the history, right, is invented by Norman Morgenstern, right? That's in the classical masterpiece in the 1930s, something like that at that time. And he invented expected utility. And same as what we learned in the topic 1, right? We give the foundation. We start preference. And under what preference, we can generate people behave as if they are maximizing expected utility. Okay. So again, we have to fix the number of outcomes. We only consider lottery by probability. Okay. And the first two probably is not surprising to you. It's same as what we assume for preference over n different goods, right? But now it's not n different goods, but over n numbers with probability. And not surprisingly, we require completeness and transitivity. I think completeness is okay, right? You can always compare to lottery. You can say which one is better for you or the same. Okay, that should not be an issue. You can't say I can't compare, right? So that should be okay. And the second one, transitivity. I think that one should also be fine. If you like A over B, B over C, then you should be A over C. So it's not something too terrible. Okay, I think that is very basic. Usually, no people attack this guy. Sometimes completeness will be there, but usually there's not something we attack. So with completeness transitivity, we can write what's called indifference, right? If P over P is no less than Q and Q no less than P, then they're rather equal. And because we can compare everything, right? And we can assume without loss of generality, if A1 always appear and AN also appear, you can rank them, right? Because you can always form a linear, put them on linear line, right? So the A1 is the best, AN is worse. And if this appear once, we don't write the 1. So that would be, that is something, the notation we use. Now, the first thing is continuity. In this framework, you often see 3 different types of assumption, and I think 2 is the one we used to say, right? When you say when X better than Y, right? We say that somewhere near X was still better than somewhere near Y, right? Remember when we learned topic 1, right? When X is the bundle X strictly prefer to Y, we say that somewhere nearby X is still can find somewhere near X, still strictly better than strictly Y, right? Continuity means that the preference doesn't change suddenly when you move around, right? Just change a little bit X, a little bit Y, this strict preference still hold. So that is the same idea here, right? I have the rotary P is strictly better than Q, right? I can always find a radius neighborhood, right? Somewhere nearby, just change something P, right? So change something be Q, then still better, right? And this is good, but this is not very good for proof. So usually look at the proof, they usually look at the other alternative definition, which is equivalent is the 1, okay? You can prove that the same. So 1 is saying, also it's actually pretty intuitive. Actually, we also use it in the proof somewhat, right? It's saying that if they're free bundle, okay, and they have a strict ordering, P better than Q, Q better than R, okay, you can always able to find, okay, a mixture, a mixing of P over R, the same as Q, right? This compound bundle, okay, over P and R, that same as Q. Actually, we do the same. Remember how we do it in the standard chapter 1, right? We find a bundle, right? 45-degree line here. We find a bundle, we find the minimum bundle, the best bundle, the minimum worst bundle, and the best bundle, and there's some middle that is equivalent, and that one is the same one. So we have the same. And right, there must exist some Q, right? Otherwise, if that doesn't happen, then there's some alpha, right? Otherwise there must be some jump. So that would be exactly something there. Okay, let me draw a graph if you're still not really clear what we are doing. All right, try to see if I can draw a graph here, right? And cannot draw it the pencil, right? Say, suppose this is P1, right? Suppose this is P2, suppose there's 2 states of the world, right? And the one simplex will be just like this, right? I mean, I should use red, right? So this is the lottery that, the red one is only lottery that we care, right? And what we have is, suppose there's a, I don't know, suppose you like PQR, right? So there's a P is here, okay? R is here, and Q is here, okay? It said there's some way that you can mix P and R same as Q for you. Okay, it's somewhat like that, right? Of course, it need not be in this order, but for a preference, if you like P over Q over R, okay, there's some way you can mixing P and R would be indifferent to Q. Okay, so that would be the idea. Okay, you are mixing, there's some way that you can mix, okay? Q will be indifferent to alpha, right? And 1 minus alpha R, right? There's some way you can mix somewhere in the middle. I don't know where it is, but maybe it's here, right? Maybe this one, right? It's the right alpha, then same as Q. I don't know your shape, all right? I don't know how it looks like the indifference curve because I didn't specify what it is, right? And okay, because I don't even assume any monotone or whatever, but this is the assumption here is continuous that imply this would happen. So I hope that explain what it is, okay? And the next one is something I think is also very trivial. I think it's trivial, right? But in experiment, that probably may not be exactly correct, but because it depends on how you think they're same or not, okay? But here is like the following. If you have a better outcome, mixing 2 outcomes, AI and AJ, okay? And only lottery over 2 outcomes, okay? Any 2 outcomes, but it's order, right? So as long as you give higher probability to a better outcome, this is better. Okay, and do note that it's strictly better. Okay, so that is it can violate in practice, right? Because of the fact that you increase a little bit, probably don't respond, right? People because do small calculation, right? But this is what we assume. Okay, I think it's very reasonable. Okay. Now another two axioms. Okay. Which shouldn't be surprise you at all. And these two axioms basically give you the idea that compound lottery can be always reduced to simple lottery, which means that you don't care about lottery itself, you only care about outcome. Okay, so what are these two axioms? First one, you said if lottery P is better than R, okay, P better than R, you mix it with Q, will have no difference, right? It's somewhat like independent of irrelevant alternative idea, right? It's just like if and only if. So this can reduce to here and this can reduce to here, right? So basically you take out things, you put it back on both sides and move the same. So that is pretty strong, right? Because we can always reduce, right? If the same, you can always add back and reduce. So that's why I can go back and forth, right? As long as P better than R, you're mixing something, then they're not. And we do know that from experiment, this is often violated because people are not machines. So when you combine things, people look at things differently. So this is usually the part that violate. And this reduction is saying that you don't care about how you do lottery, but you only care about the outcome. Okay, I give you a big lottery, but I just reduce it by giving you the only care about the outcome. Okay, they're the same. Okay, so example would be like this, right? In the case, suppose you have two outcomes, right? You give me two lottery, and you consider a case where you would 0.3 you pay lottery 1, 0.7 lottery 2. Will be same as instead of doing this, I do care about the outcomes, and I say outcome 1 with 0.34, outcome 2 with 0.66, same to you. So I don't really care about lottery itself. I care about how likely I get that outcome, right? Because I calculate how likely I get outcome 1, right? 0.3 I'll go lottery 1, and 0.7 I have lottery 2, so it's 0.3 times 0.8 plus 0.3 plus 0.3 plus 0.2 and 0.7, 0.4. So that's how you get the first item there, and the same the second item, right? It's just like, I don't care how I get there. I only the outcome oriented. I don't care how I get there. Okay? Means that I really don't have the framing problem, right? I really don't care. I get rich, go to casino, all right? Or I get rich by hard working, right? Or I don't care about how I get A from this class. Either I study hard or I just cheat in the exam, right? As long as you give me the same outcome, it's fine, okay? So of course, this is very strong assumption for this one. First, you assume the individual is able to compute this probability, which usually we don't, right? And you don't care the path you get there, then sometime the path would be important by itself, right? The mean is so more important than ends, right? Of course, here it's just outcome oriented, okay? And that is something different. Okay. So turn out the monotonicity is actually implied. If you have independence, you have monotonicity, right? Because that you can always subtract the useless thing there, right? Right, because then you can get them out. You can prove that. I'm not going to prove it, but that means that independent is very strong. Okay, the independence is very strong. Okay, because independent implies monotonicity. Monotonicity is also a very strong idea. Okay. All right. It is a proof, but I'm not going to prove it. Okay. what I want to turn your attention on is this classical result. This 5 axiom imply that if an individual follow this, okay, you can have a utility function over lottery, okay, such that this can be represented by your utility over the outcomes, well, not the lottery. Okay, each outcome, certain outcome, you can form utility over them. Okay, and then just weighted by the probability, right? So basically, what we are saying is, okay, we only need to tell us all possible outcome, what my utility is. Okay, there's no probability. Okay, I just need to say utility over outcome, which is classical, right? There's no uncertainty in this world, right? All possible outcome, you tell me. If you get me this outcome, what's my utility? Okay, and my utility over the lottery, we just take probability over all the utility there. That's what expected utility means, right? So, and because of the last 2 axiom, compound gamble reduced to simple gamble. So basically, everything can be reduced to this the simple form, and that makes our life easy, right? Because this is rather easy to compute, right? And expected utility, of course, go way back before Werner Morgenstern, right? But we'll talk about that soon. But that is, but they are the first one to provide the proof that these 5 axioms deliver expected utility. Okay. I want to talk a little bit about the proof because I think that this proof is rather important. But I'll go quickly because it's not. You can see the gray area, gray color, so it's not something too important. Will be in your exam or what? But I want to show you the proof because this is important proof. I mean, we skip so many proofs, but we can't skip all, right? Because otherwise it's not a graduate class. So we have to keep some proof, okay? Just for yours fun, okay? This one is very easy, okay? This is a trivial proof. This is saying that, okay, if all outcomes are the same, then you can assign every outcome utility 0, then I'm done, right? Because if the best outcome, same the worst outcome, right? The easiest thing is to set all the utility to 0, then everything is 0 no matter what you do. So done, right? Because everything is same to you. No matter how you mix different outcomes, it's same to you anyway, right? So this is trivial, right? But this always appear in the proof, okay? Because you have to close a loophole like this first, right? And then we can start the proof with the first one is indeed strictly better than the last one, right? Otherwise, if every outcome is the same, then the proof is simple, right? So we go with the more serious case is the first outcome, the best outcome is strictly better than the worst outcome you care, right? And now the first part is very simple, right? Same as actually similar to what we do in the certain world, right? Every outcome can be written as a lottery over the best and the worst, right? Is that clear? They say alpha, okay, right? If of course, if you want to be more precise, it's alpha I because every action, every outcome would have an alpha, right? This one is unique, right? Because monotone, right? Increase the alpha actually would change another, right? So that means that we can write this alpha as utility, right? Actually, it's very similar to what we have been doing in the certain world, right? Same. You just remember how we do the minimum, the maximum, right? Do the same. The difference here from before is we don't fix the final number of thing, right? That's always right because remember how we do the proof in the. If you still remember the proof, I don't know, you still recall the proof we do, right? If you recall the proof, we have x1, x2, right? And what we do is for this bundle, we go to the worst case, right? But say suppose I want to look at the bundle A, right? And you go to bundle B, which is slightly worse, right? And go to bundle C, that is slightly better, right? And by continuity, you can find some bundle here, okay? That is in the indifference curve for you, and this is a unique one, right? And we say this bundle, 45-degree line, can be represented by a number, and this number with utility for this bundle, right? So for each bundle, you can construct this. But now we don't have this luxury because of this is much more complicated. But still, the good thing is, I look at everything you pick. I can look at the worst case and best case, and also find the same number there. So that number will be your utility. Okay. I hope you can see this is a very similar proof. Okay. There's nothing. That's why I want to talk about this, because this proof is so similar, right? And you can say the best case is 1, the worst case is 0. That fixes things. Okay. That means that if you do that, you can always rewrite I outcome is a compound lottery. Right? Is that clear? Right? Because this is 0, right? This is 1, right? So that's why you can multiply. This is 0, right? 0 times this gone, and this time this is just itself, right? So you can rewrite this. Okay? So that means that no matter how complicated the model is, right? You will just simple lottery. It just means that you reduce to a number. Okay? And the fact that independence means that you can mix any of this, right? Mix any action is same as mixing that. Right? So that means that if I had simple lottery over all possible outcome, it's mixing over all this. Is that clear? So say action 1, right? So outcome 1, so outcome 2 will be some combination 1 and 2. Outcome 3 will be some combination, right? In general, the general lottery will be mixing all the outcomes, but can be written as mixing 1 and n. Right? Let me repeat, right? Because every outcome can be considered as compound lottery. Sorry, you consider as simple lottery over 1 and n. Okay? And if you consider lottery over n outcome, then it's a compound lottery. Okay, maybe I write that down. It's a little bit, maybe a little bit difficult for you to think, right? So what I have done is, if A2, A3, up to AN, right? Okay. Okay. And I say U of A1 is 1, right? And I say U of AN is just 0, right? And you map anything in the middle, right? By okay, A2 is some combination of A1 and AN, right? Because we exist some number there, right? And that means that A2, right, is equivalent to U A2, right, times A1, right, and 1 minus U A2, right, a lottery over that, right, times A2, so AN, right. But anyway, right, so that would be the case, right? But this is 0, right? So this is gone, right? So that's why every outcome, right, can be considered 1 and n, right? And now the question is, we have general lottery A1, P1 up to Pn, right? But that means that this is a compound lottery, right? If you get A2, it's actually choosing 1 and n, right? So everything is becoming 1 and n, right? You only care about whether you get the probability getting 1 and n. So everything can be reduced to 1 and n, right? So that I hope that is clear what we are saying, right? Because every outcome is P1N, right? And if you lottery over all possible outcome, it's a lottery over this kind of lottery, and then just 1 over n. Okay, I hope that is clear. Now, what remains is to show, okay, that is actually representing this preference. Remember, when we say this representing preference means that if you like lottery over the other, you would have assigned higher probability, right? What we have just shown that it just, okay, this is same as this, right? But we didn't still show this actually is the number that they care, right? So that's why we do the final part of the proof, which is trivial, but it's okay. So if you like this, okay, because this equivalent this equivalent to that, right? And remember the monotonicity, they are lottery over 2 items, okay? And this is better than this guy. So we say if this better than this, it must be the case that this is more likely than this one, right? So this is likely than this one. So I'm done, right? This is what we want to prove, right? Because you want to construct a case where you have high utility, right? You like this one is based on this number. Okay. So that is, we do the proof, we've done the proof, it's very simple, right? There's nothing new here, right? Just basically, again, is to, the idea of the proof is like very simple, right? You have a best and worst outcome, okay? And every outcome can be considered lottery over this and best and worst outcome, okay? And any lottery actually can be reduced to lottery over these 2 outcomes, okay? It turned out to be this related to this number, right? So it's very genius proof, of course. That's what we do. I mean, this is the standard view. Okay. Do note that this expected utility, right? You can see is a linear improbability, right? And of course, in general, you can imagine the case actually is non-linear, right? But that would be beyond expected utility theory, right? It's a probability weighting, right? I mean, you learn reference dependent, those things deal with non-linear, but it's out of the scope of our class to focus on those. You make some other less restrictive axiom, you would allow this to be a function. Instead, linear of P can be a function of P, but that is out of the scope of today's class, because you make strong assumption, right? In general, the theory is like you make strong assumption, your functional form is more restrictive, right? If you relax some of the assumption we make here, then become more general. So that is what decision theory people do, is try to figure out, weaken all these assumptions, which one to weaken, and will give a more general form. Okay, and then that is whole literature of decision theory, is try to figure out, okay, if I take away this assumption, then this form will be getting more general. Okay, but since I think you are not doing the proof anyway, basically when you do experiment, will be something look at the literature, right? Which type of axiom would lead you to which kind of preference form or utility function form, right? Then you're going to test the axiom or test the hypothesis directly, okay? But I hope that gives you the idea why this is true, okay? And I hope the proof is okay. If a question, you can ask me during the break. I think this, it took me quite a while to understand what's going on here, especially this particular part. But you write that down, then it shouldn't be too difficult, okay? And after the break, we'll talk about some property of this what we call the expected utility theory, and then we will continue to look at some risk preference and how to compare them, because we will need them, especially in the finance application, or when we do contract theory that we're there, or when we have income information setup. this is something we will need. And let's have a break of 15 minutes, and then we'll continue our journey on all the math going on here, okay? So especially for those who haven't learned it in undergrad, or you forget them, then you'll be a little bit difficult. But if you know very well, then this will be a good revision. But we give you some proof along the way, because I think you must have learned them in English or in verbal sense in the undergrad. But I try to give some proof why we have that, and then especially for people who do accounting and finance, or that would be something that they have learned it well already. But I just give a little bit background revision for that. Okay. Have a break of 15 minutes, and then we come back. So we resume at using the clock on the here will be 13:27. Go around to see if any question, but I guess you don't. But anyway, go around. So let's get back. I know this, if you learn it, it's really familiar to you, but as we said, the advanced class is going to give you some foundation. Okay. To reiterate why we need to learn foundation, because some of you actually doing experiment and doing empirics, then that would be something that actually you do, right? Expected utility, I guess everyone knows it, right? But why I bother to talk about axiom, right? Two reasons. One is you do theory, you may end up with, you want to investigate new axioms, right? And that is axiom we have, right? It's like continuity and all these 5 axioms, right? This kind of thing, right? And changing this axiom will lead to different result, right? And then probably you know the famous paper, right, reference dependent, which Daniel Titman and the co-author, right, just get Nobel Prize because of checking these axioms and figure out that it's not doesn't fit very well, right? And then write another new models, right? And then they get Nobel Prize for that, right? And that is the reason why we want to do that, right? For empirics, and then you will probably also look at uncertain world, and probably you may say, okay, maybe your empirical result doesn't fit very well, right? Using classical model, right? And probably you may want to use another different type of utility model to fit your data, right? And that is entirely possible. So you need to learn the assumption behind the utility function, right? In order to say whether your model apply or not apply. So I hope that makes sense. Okay. So very quickly, this only property that we didn't talk, but this is a very simple property for utility is now utility is no longer ordinal, it's cardinal. Cardinal in the sense that you can only multiply by constant plus a constant that remain the same. If you take a square or whatever non-linear, then will be different. Okay. And that means that different from the previous case, when you run regression, you can't really take a log, right? Take a log is another thing, right? When you understand when you do the topic one, right? Utility over lottery, sorry, utility over commodity, right? You run regression, you try to estimate utility function or whatever, it's fine. You take a log, it'll be okay. But if you talk about uncertain world, you take log on utility is a different thing. Okay, so that has to be careful, right? So that's something has to keep in your mind when you try to think about this. But just when you do regression, you will know. Okay, I'm not going to go too detail about that. So one of the important function for model uncertainty is application in finance or accounting or business application, right? Where you have to make decision for the future event, right? Or same for environment, right? You don't know how the world is going, right? Whether the temperature net zero will be there, right? Because the world is changing at all, right? What is the boundary of the environment is not clear. Okay. But as I said, we focus on finance application or asset pricing, right? That in that case, we usually focus on money, right? So the set of outcome is just can be represented by a number, real number. This graphic R will be number line, okay? And then we focus on everything's continuous, L, right? And then our world can be described by the CDF big F or PDF F, okay? And here I make a big jump from discrete to continuous sometime, okay? I mean, of course, discrete apply, right? But we just jump to assume that continuous also apply and the limit. There's somewhere in the proof to do it, right? Because you may ask, right? If the proof for expression is so simple, why we need von Neumann to prove it, right? I mean, of course, they do a very general approach, but we prove it's the simplest version, okay? So in that case, we will write the following, right? We assume it holds for infinite possible outcome. So utility is with integration, right? Instead of summation sign. So we just assume everything goes through, okay? If you want to know the detail, then you have to check papers, okay? So the first thing to look at is expected value of gamble, right? And the expected value of the lottery, right? It's just the value on expectation, right? And we will say the gamble is fair, means that on average, you're not winning or losing, right? And that is the idea. Okay, this is the idea of the gamble. And actually, there's a question actually start if you look at probability theory. And people study this is question is whether how we value a fair gamble, right? Is it the case that because gamble to be fair, right? Then it's the case no one should pay for it, right? No one pay to play, right? So, all right. So suppose we go to casino, right? Can we charge people go to casino, right? Because suppose casino is fair, right? Can you charge people for entrance fee? That is actually people asking in old days. So suppose you go to gamble, right? And you have some return, then how much I can charge for the gambling, right? What's the fair value of this gamble? Because that is the old day, these classical mathematicians, they study. And actually is, I think this is the very famous paradox, it's called St. Petersburg paradox, but this is not by Russian, but rather by Viennese, right? It's by the famous people who are probability theories. The question would be the following, okay? You consider the following lottery, okay? You toss a coin, okay? If a head appear, the game end, okay? The first is coin is head, you win $2, okay? If you get a tail, continue to flip. If second is head, you get $4. If continue, you get a head again, then you get $8. Every time you multiply by 2. Okay, so basically just like I put $2 here. You get a head, you get it. Okay, if not, you get a tail. I put double the amount, become $4. You get a head, you get it. If not, then you go. Go on is 2 raised to the power n, right? Okay, and if you win the first time, it's 1/2 probability, right? The second time is 1/2 times 1/2, right? So the expected value is just this, right? It's 2 times 1/2 of raised to the power I, right? So it's just summation of all the 1, that's infinity, okay? The question is, this payoff, right, will be infinity, right? So suppose you play this many times, right? Many times, you got infinite amount of money, right? So the question actually is also the empirical question. Actually, probably if you look at experimental textbook, this is probably they will say this is the one of the earliest experiment, okay, done in the history, is to ask people how much they pay for that. Okay? And turn out, how much you want to pay for that? To be honest, are you going to pay $8, $2? Or I guess everyone will pay at least, right? $4 probably, maybe, right? Depends on how risky, but 8 may be okay. But I think no one will pay more than $10 in general, or 20, or right? At most 100, right? No one will pay more than 100 for sure, right? I guess unless you are very super highly risk loving, then otherwise we'll define risk loving. But only you like excitement, right? You would not ask for more than 100, right? And what does that mean, right? And the question is actually we just saw here is, we are not, when we evaluate lottery, right? It's not expected value it matters, right? Because we have diminishing utility for money. Okay, that is what it said is because of you make when I is very big, right? And it's very far away, and the probability is very small, right? And the idea is this expand because this expose, right? And if this is a concave shape, and this will converge. So the way that economists think is, okay, the probability cannot be play around with, right? Objective, right? So the play around is they don't value $1 for $1, $2 for $2, right? Maybe okay when you increase $1 to $2, maybe you have a lot of utility, right? But when you have 1 billion, okay, give you $1 more, probably a little, right? So it means that it's a kind of concave shape. When it's concave, it's sufficiently concave, then this is finite, right? So that solves the problem of finiteness is to make this concave. But by making this concave, that means that you have your utility, right? It's no longer linear, right? You have to include the term utility, right? It's not, you cannot just use money as the end. You have to say something, you look at the money differently according to the amount, okay? And in particular, you look at, as we said, the very first experiment they look at is egg, okay? And you do the math, turn out to be, this is same as the best guess is the log utility, okay? Your UX is log X is the best fit for this data, okay? So I guess this is one of the earliest experiment, right? Because they keep people asking more than 8, and that fit, I mean, by experiment, actually, I mean, the old days, actually, the people just ask around and figure out this is $8, around $8 on average. So that is one of the earliest experiments. Okay, and that's why log utility is well before the Werner Morgenstern. I mean, this is at least 300 to 400 years ago. Okay. So then that the St. Petersburg paradox is trying to see when we have actually the diminishing utility of money. Okay, indeed would imply that actually later you see imply that you have risk aversion. That's why risk aversion is more natural. You hate risk. Okay? That's the beginning of all the insurance, all the diversification, right? If we really like risk, then we put all the egg in the same basket, right? Not separated. Later you see when with diversification, this is the reason. Okay. But first thing is risk neutral. Risk neutral, the definition is utility on your lottery is just your utility on the expected value, which is fixed outcome. That's the money wise. So it's just like this, right? And this is often used it when you talk about you have a lot of money, right? The lottery is small to you, then you use it. Okay. And when you look at application in finance accounting, this is often assumed for big company, right? Insurance company is assumed to be they're risk neutral, or big investor, institutional investor is risk neutral. Okay. Of course, everyone is risk averse, but in terms of math, your life is much easier, right? Later you see this is very simple, right? Because you just reduce lottery to the expected value, then you're done, right? And together with, say, assuming they are following normal distribution, then the life is very easy. Okay? This is mostly commonly used, even in a lot of application. Okay, risk neutral is a good thing to do. Okay. The first thing to prove, probably not to prove, but it's very simple, is a risk neutral. You have a linear, right? You're linear in money, right? Linear in utility, right? And this is possible only if this is because this expected value, right? So only linear in your linear function. Okay. So it means like this. The reason, the proof, I'm not going to do the proof, but I just the graphically, right? U1 is like this. This dot here, U3 is here. Okay. If you consider a lottery over these two, half and half, then it's here, right? And because you get 2 is also here, they must be on this point, so it must be linear, right? Is that clear? So utility of 2 must be same as this guy. It must be the case is linear, right? Because how you mix the same, so no matter how you mix it here, should be same as here, then that's the only thing they can do is linear. Okay. Now the other one is when we have St. Petersburg paradox is your utility of the lottery is less than utility over your expected value of the lottery, right? Is St. Petersburg paradox is infinity, right? Then what we said is right is less than that. Okay. And that's definition. And we want to show you probably learn, right? It must imply your utility is concave shape. Okay? By concave shape actually means that you have diminishing utility, marginal utility of money. Right? Concave means right. Additional money actually means less to you. How do you prove this? This requires injected inequality. If you do finance, this is very familiar, right? But I'm not going to prove it. But basically, just like when you integrate, then you take integrate u out, then must be less than that. That is causation inequality. But I'm not going to prove anything. But it would this would imply that U is a concave. Okay. Now it doesn't prove, but let me show you the graph, right? If you here, right here is the U1, and this is U3, right? If a fair lottery, right? So be over 1 and 3, right? Expected value of the lottery is 2, right? And value of 2 is here, right? If I give you the expected value of the lottery, right? If you're risk averse, you would prefer give you a fixed number rather than ask you to play this too, right? What we mean by risk averse means that I pay you the expected outcome directly rather than ask you to play the lottery game, right? So you play the game, then it's average of these two values, right? Just in the middle of the height, right? Turn out to be less than that, then it's concave shape, right? I think this is easier to say, but to formally prove this requires Jensen inequality, but we're not going to talk about that. Okay, that would be the proof. You can check the book always like this. Okay. So without any proof, you can imagine if you're risk loving, you rather do the lottery rather than giving you the expected value, right? That would fit the idea when you go to casino or we do lottery ticket, right? And that is without any proof, you will see this is the case, right? Same as before. This is the value that asks you the lottery. This I give you the fair value, and this is the convex shape. Okay. And so you probably would ask the question is, are human risk loving or risk averse, right? Because we simultaneously saw people doing lottery and simultaneously people buy insurance, right? Buy insurance risk averse, right? And do lottery risk loving. So are we expecting, what should we do, right? Because we can't simultaneously explain both. Okay. And there are many ways to explain this. Okay. There are many theories. One theory would say people are risk loving when the bet is very small, right? Because lottery ticket, you pay a little, right? The gain is a lot, right? So that's why you will be risk loving in that sense. Okay. And when you buy insurance or you diversify because the last thing in stake, then that's why it's risk averse. So big thing we're risk averse. For small thing, we're risk loving. Okay. Of course, if you use a reference dependent, there are other explanation. You go to finance, they will talk about kurtosis, about skewness and also important, but I'm not going to go to that route. But there are many theory, more than one theory. I mean, at least to explain all this thing together. But I'm not going to go. Look at the literature. There are many ways to explain all this thing. There's a consistent way to explain that more than one theory, but I'm not going to go about that route. And in most of the application, we will assume risk aversion because, as we said, right? Because I think all of us don't like risk, right? Otherwise, right, we have to get paid to buy insurance, right? We always want risk. We really hate wandering around. Okay. So now I guess we can talk about risk premium calculation, and also we can talk about expect later we will arrive this risk aversion measure. Okay. So that is the thing we want to talk about. Okay, and we want to decompose the risk premium. Okay. So so we said in general people are risk averse. So the question is how can we measure that? How can you quantify that? We know people risk averse. How can you quantify their risk aversion? Okay, except from data, right? You in the experiment, you cannot ask them that what is the risk aversion, right? I mean, you're measuring in some way. So one way, of course, is to look at the risk premium, right? And asking how much they're going to pay or kind of sacrifice to avoid taking the lottery, right? Because that is the part that they're going to pay, right? So the definition is very simple. So here, big U, W over L is ask him, start with the wave W, right? And pay lottery, okay? So this is the part that I asked him to pay the lottery, right? This is what the utility get, right? Expected utility from paying lottery, okay? And now I say, okay, fine, you don't like lottery, okay? So what happened is you start this wealth, I pay you the outcome of the lottery, okay? I take away some money from you, okay? Which money I take away that make you same, okay? And this one of the way to measure, right? Because it's really easy, right? Because the larger the money, right, the more risk averse you are, right? This is the easiest measure you can come up with sometime in an experiment, right? You give a lottery, right, of two things, the price list approach, right? You give two columns. One column is asking how much money you want to get for sure. The other one is the lottery, right? And then changing this number, then I would know your risk premium, right? That's the easiest way to measure, right? This often used in the experiment, right? List of price, or you input a number, that may be different, right? Can be sliding slide or just tick, 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 right? And this. And of course, you can do the same, but we write this certain equivalent, which means that this amount of the final number you want, same as you do a lottery, right? So this is called the equivalent, right? So this basically means that, okay, this number that I give you for fixed, okay, this the higher then is you get, right, the lower the risk premium, right? So they're inversely related, okay? So they are related in this way, right? So there's nothing very deep in this here, okay? And I think the deep part is try to look at the graph. That would make your life more easy, right? Again, we assume we start with the risk aversion, right? Asking 1 and 3, right? And as we said, this is expected value of the lottery. If I give you this, then you have this utility here, right? And if I ask you to pay the lottery, that is the utility you have, right? This is a lottery that this is the value of utility. If I ask you to randomize 1/2 of 1 and 1/2 3, this is how you think you are, right? This is the utility level, okay? And then if I give you this amount C, right, the intercept, right? This is, you would be indifferent between paying the lottery or I pay you CE directly, right? And the difference between CE and the expected value of the lottery is pi A, right? It's the risk premium, okay? So either you look at the risk premium or look at the CE, the same, right? As I said, they're inversely related, right? If you move this one further, this one's larger. That's why I said they are. No matter which one you look at, it's fine, okay? And this is a way to measure your risk preference, okay? Is that okay? Is that okay that we have this? Now, is that okay? Is there any question? C is the money that I give you. C is, okay, you have C at the end, or I ask you to pay the lottery between 1 and 3. You 1 and 3, then you get this expected value. You plug it there, C is this one, right? And risk premium is the difference between the lottery outcome and the CE, okay? Of course, I already assume the W is 0 at the beginning, right? Or you can say W plus X is here, but I just make their life simpler, right? Start with them. Now, sometimes you would also look at the case where you don't look at absolute premium, but look at relative risk premium. Why I want to do that is people usually may not focus on the risk aversion. It's not about absolute. It's about percentage of your wealth, right? And that is how people would care. And these two ways of viewing the risk will lead you to two different class of utility function, which you will see later very soon. But this is very common, so that's why I want to mention it. Okay? And you would think the loss is a percentage of the wealth, so that's why lottery is you lottery over percentage of your wealth, T times W. Okay, if T equal 1 is mean low loss and gain. If T bigger than 1, you're gaining. T less than 1 is losing. So then when we write this, the random variable we want to care is T. Okay, it's not L by itself. T is more important. But anyway, we can write it this way. Right? So we'll define this way. Okay, our risk premium is the same, but it's percentage of your wealth, not absolute. So the only difference you can see here, this L is percentage of is this time the wealth. It depends on the initial wealth. Is that clear? So look at previous definition. Previous one is just minus this absolute amount, which independent wealth, right? But now we define this in this way. Okay. Okay. And just rewriting why we do that is just basically the absolute premium and the relative premium is different by W. Sorry. So okay, it will that the risk is not minus, it's multiply. It's not minus. So before it's W plus L, right? The uncertainty comes from you subtract or you add. The part is like you may win something or lose something. Okay, but in finance, probably you put the money there. Is the you think about uncertainty is like the in terms of percentage, right? Say the T is the part that varies. It's relative to your wealth. Is that the same thing? There's nothing new there. Is that defined in this way? And later you will see why we do that. I mean, the reason is whether we assume this is constant or this is constant over wealth. So that later you will see. But this is the part that is okay. Because before that, we assume that our uncertainty is this plus this guy, right? But now we assume our wealth is. Oh, I see. Oh, I see what you mean. Oh, I see. Oh, I see. You should say T should be equal to 0, right? Oh yeah, T should be. Yeah, T should be 0. Yeah, T should be 0. Yeah, you're right. T should be 0 for this one. Yes. Yeah, because that's how I define this one. Sorry, this T should be 0 here. My mistake. Because it's gain and loss, so when T is 0, there's no gain and loss. Sorry. Now I get what you're saying. Okay. Thanks for correcting me for this one. So why this is important? Because you will see as a matter of fact, right? Because we want to decompose risk premium into two different parts. One is the riskiness of lottery, the other one is with preference. Okay, and turn out to be this decomposition is very useful. And that leads us to we call it a head arrow measure of risk. And that is we often use in the literature and the calculation. But let's see. Okay. So I think that need no explanation. This is the variance of the lottery, right? So this is we are in the grad level. This is something simple. So the main thing is the following. Okay. So this is the arrow. I mean, the Kenneth Arrow, the famous guy, right? Who invented this is your risk measure is how concave we are, right? If more concave, the function is more risk averse, right? So the more concave is they are more risk averse, right? So that means that your measure should be related to the second derivative, right? The more concave, then, right? Because if linear, then the second derivative will be 0, right? If linear, right? But concave is negative, right? So that's why you're negative here to make it positive measure. Okay. And the reason why we want to do this is because we want to normalize by our marginal utility. Later you will see why we do that, but this has some definition why we have that. But let's assume we want to normalize it. We will explain why we need to normalize it. Okay. One of the reason is because of our utility function is same under affine transformation, right? Because remember, ux times x and vx times 2x are the same thing, right? So we divide it by this, then regardless of utility form, then the same thing. Okay. And we want to compare different individual. Okay. You give me two utility function. I want to say which one's more risky. Okay. And this measure, okay, if you give me these two, they're the same. Okay. So that would be the first reason we're going to divide it. Now we give you the idea why we need them. Okay. Why we need to do that? It's because turn out, okay, for a small bet, fair bet, okay, and the bet is small enough, okay, your risk premium can be decomposed into two things. One is the variance lottery. The other one is absolute risk aversion. Okay, that means that when you do an experiment, okay, you go to the experiment, look at people's risk premium, okay. As long as you fix the variance there, then you have a good measure of this guy. Right? As long as your bet is not too crazy, right? And I think it's fine, right? Because in experiment, the reward you give in is very small, right? So this is as long as bet is fair, right? So you can actually decompose it into two parts, right? And that explains risk premium. Why it's important? Because risk premium is what we observe in the real world, right? Look at different class of stock or different type of bond or different type of stuff, financial assets, then you can look at the risk premium, right? And you're also able to come up with different right? Look at historical data, right? Different possible way of payment, right? But looking at this, I can fit to the R. I can measure that, okay? And remember what's RA? RA is the utility shape, how concave they are. So you can actually understand how concave they are in experiment or using data. Right? So that would be one thing, right? Because that's how you connect, right? Because you can only observe risk premium, right, in the real world, right? You can also observe the variance, but by that you can back out the shape, in some sense, right? So the proof involves some basic algebra, but I'm not going to go about that. So why I want to do that is because this, okay, if you assume people have constant absolute risk aversion, okay, that means that no matter what is your wealth, okay, no matter what's your wealth, if I'm asked to do the same lottery, my risk premium is always the same. Okay, suppose you ask me to play a lottery. It's a fair lottery. Say if I have a head, I win $1. If I lose $1. Okay. And then if I'm risk neutral, that's fine. I'm going to pay whatever. Don't give me money. But if you I'm risk averse, I'm going to pay say 50 cents to avoid this lottery. Okay. Then if I have a constant risk, absolute constant risk aversion means that no matter what the wealth I am, right? No matter I have $1 million, I have $1 billion, I'm the risk averse, the certain equivalent or the risk averse risk premium I need to pay for that is same. Okay. So this is the form, exponential form. Okay. It's the one we often assume. So this is explain why this you see in the literature all the time. Okay. Do note that you cannot take log to this one, okay? Because you cannot do any transformation except multiply or add the constant. Okay. So that's why sometimes you will not see the C here. The C is gone. B is usually 1, right? A is also 1, right? Negative e to the negative x, right? It's the one that usually you see in the papers. Okay. Okay. And this is the first one. Okay. And the second one we have is, okay, we look at the risk in terms of percentage. Okay. And if you write in this way, you write U tile T, okay? Then when you differentiate with, okay, respect to T, okay, because T is the only part that change, right? So that will go W out and W 2 times W out, and you cancel them and you set T equal to 1. Focus on the fair bet, right? Because no matter what you get, then T is you're going to get the same. Okay. In that case, you can define this relative risk aversion. Okay. And okay. And this is the risk aversion that often used. Okay. And you would ask why you care about that. One reason is like the absolute, so the relative aversion can be decomposed into 2 parts. Okay. One is the variance, the other one is the relative risk the risk aversion measure. Okay. So again, it's basically decomposed in 2 parts. I think I did the proof here, but I think that is the most useful in this guy. Okay. If this is mostly common in the literature, right, is the special case is a log utility, right? And I have mentioned that this actually fits St. Petersburg paradox the best. Okay. And in general, this is more general than this, the law. Is this AX1 minus B times C? Okay. And sometimes you will often more see this guy, right? In the finance literature, this is something very common, and usually they're lazy, and then they would just even cut the 1 minus B. Okay? They would just x raised to the power theta, and that's it. Okay. And the log is also very common. The reason why I want minus B here, because B is the absolute risk aversion. Okay. So that what we're doing is to give you the foundation. Why in the literature you often see this assumption, and because what we're making is that either you assume constant relative risk aversion or constant absolute risk aversion here. Okay, either way, then that's how you derive the formula here. Okay, and that is we often use this. Okay, your utility is either following this one or the other one. Okay, is that okay? So log, I think the most common is log utility. So that is you can often when you derive formula, this is the one you use. Okay. So let's have a break of 15 minutes, and after that we will talk about very quickly about compare lottery. Why we do that? Because these two often appear in literature of when you are comparing two uncertain outcome. Okay, you would use this stochastic dominance. Okay, because before when we look at the lottery, okay, we can say people like this over that, right? And different people have different tastes. Then it's captured by the risk preference, right? Because some people prefer the risky one, right? Require higher certainty equivalent, right? That is basically comparing people's, okay? But also we can also look at, keep the same person, look at how he liked the different lottery, okay? Let me repeat, right? Risk preference is asking I have the same lottery, look at different person, right? And look at how people would like to pay how much, right? Look at the risk premium and risk aversion. And lottery is, common lottery is like I have two lottery, right? And look at the same person without telling me his or her particular preference, can we say something? Or it's more robust comparison, right? Because we want to say, okay, first order stochastic dominance is without telling me your risk attitude, right? Without telling me whether you're risk loving or risk averse or risk neutral, can we rank the lottery? The minimum assumption approach. And second order stochastic dominance is assume people are risk averse. Can we come up with an ordering of lottery? It's a partial order, right? Ordering the lottery them so that you can say one lottery better than other, regardless of how risk averse you are. Okay. And when we have risk preference, it's more sophisticated, right? We exactly pinpoint how can estimate how risk averse you are, right? Try to estimate, right? But here it's like usually when we look at compare lottery, it's like gives you an idea that for sure, right? It's more robust comparison. Okay? But let's have a break of 15 minutes and then we come back to continue. Let's resume at 12:28.
你就不用上出来，划掉表之后别上去，你就集体打掉出就可以了。放在当时没想到，我也没想到。关心我，关心我对我来说，上课的时候，上课对。 哦，东西是可以做做钢铁，做很多，但是市场很大反应的。他说呢，现在是这个样。一方面就是找什么不叫做伟大的一次，如果要这个事情就是这，从来都没有干净的作为回讲。这边没什么意思，没什么意思。那团体赛的到了，那非常多有在，有的在上班。一个小时，我一个小时。所以是每天都用高铁上。这个我有一个学生他。他就是在这个没有我的其实他为了让我们更好吧，就是高级的一个是，我在高速的他大概在4个小时。对，所以把他那个。还是都比较那个里面在中远经文这个道理。对啊，还有是他上班那个学校在东边，他有西边，他上班的时候也过去了，就在那个玩。太远了，没办法。哦，闭着口。我想过这个是 A， 然后当时那个太远了，在海的那个太贵了。
So maybe we can continue. So before is like we keep the same lottery and compare how different people like it or not, right? How with premium then pay for that, right? The next one is look at the can we compare lottery? Okay, can tell us something, right? Because we know people risk averse or more than not, then as long as they like money, then probably we can still give some partial order, okay, some ordering, not complete, incomplete ordering. Okay, so the idea is the following. Okay, can we say everyone would like one lottery over the others, regardless of whether risk loving or risk averse? If so, actually we call this is FOSD, the first order stochastic dominance. Means that even you're risk loving, the other guy is risk averse, we behave the same. Okay, we would like one lottery over the other. Okay? If that's the case, then it's called FOSD. Okay. So we want this to hold for every possible U. Okay. And in that case, this is only possible if this holds. Okay. It means the CDF. Okay. F is always less than G. Okay. They're the same thing. Actually, this is the key. I mean, of course, this is a very interesting proof, right? You can check the textbook, but this is the same definition. And by definition, it means the following. Okay. For every possible value of number that will be realized is F is below G, then F is better, right? Because at the end, they reach to 1, right? That means that if you like more money than less money, F is better, no matter whether you're risk loving, risk averse. Okay, so that is the red one is better than the blue one, right? Okay, so and that's often the case. We want to check whether people are. That is, although it's very stupid, right? But we do this in experiment as well, right? Because we want to check whether the guy are normal, right? So we really want to check if they are satisfied this, right? If they don't satisfy, then obviously that guy probably is not have either they have some special thing or not, right? This is something standard check, right? Or you may want to say, obviously G F is better than G, right? But maybe G is simple lottery, F is compound lottery, right? And if you want to say, right, the reduction may not be so clear, right? Then if this is violate, right, obviously the reduction of compound lottery to simple lottery is problematic. So this is something you can be used to check those kind of assumption, right? The next is we can see from the previous one, it's not really meaningful, right? Because you require one thing, you require for every point of X, this is true, and that means that this is usually not possible to have, right? It's always impossible. So can we do a more general comparison? Okay. And are we able to do better is to make a more restriction on the lottery compare. Okay, the restriction we try to put on is okay, two lottery the same mean, okay, and we require that only hold for concave utility, means they're risk averse. Okay, so what I want is I only focus on the individual that's risk averse, regardless of the risk preference. Okay, I don't like risk neutral. Risk neutral is simple, so I can take it out. Risk loving is also problematic. I take it out. I just focus on risk averse. But I don't know the risk aversion. Okay, then I look at all the lottery. They have the same mean. Okay, can we order them? Okay, can order them. The answer is yes. Turned out to be not surprising. Okay. And turn out that, okay, if the same mean, okay, and as long as the CDF is the area up to any point is less, okay. So the idea is like this. Instead of saying that f is below g, but rather you integrate the function to whatever point you want, f is less than g. So you allow some intersection, okay. And this implies that if regardless of your risk aversion, as long as risk averse, you like f over g. Okay, you still can compare. Okay, so that would be the idea. Okay. And of course, you will still say, okay, how can I check this, right? Because it's difficult to check anyway. So turn out to be, there is one thing that easy to check. It's called the mean preserving spread. Okay. You don't need to compare two different distributions. Okay. And if the lottery follow F, you add a noise, a white noise, right? If you econometrics, this is called a white noise there. You add them, okay? And this is a mean preserving, keep the mean, spread is more spread out, okay? And if you spread out, then it's actually being stochastic dominant. Same mean, okay, imagine the same mean but bigger variance, right? In some sense, right? And they're the same thing. So in some sense, the finance literature focus on mean and variance approaches have some idea behind, right? Look at two investment, they're the same mean, I want the lower variance, right? That is why people look at mean variance trade-off, right? Right, you look at the same mean and then if mean efficient frontier, right? In the finance is focused on is look at the same mean, we pick up the variance as lower one, right? And that is this portfolio suggestion they suggest, right? Just want to minimize the variance, right? If given the same mean, it's sufficient. So that is what this is what we have here. Okay, so that explains that. Okay, if you take the finance class, then we'll talk about this. Okay, and now we want to talk about some application that often you would see in the literature. Okay, in the finance, accounting, or some application in supply chain or other decision-making environment. Okay. And in application, usually we only have a good estimate of mean and variance, right? We don't have more high order like kurtosis, skewness, that is very difficult to estimate. It's easy to estimate the mean and variance data. Okay. And the question, is it possible to have a utility function that based on mean and variance? Right? In the financial literature, right? We have a mean variance optimizer, right? And if that's the case, our life will be easier. And this is often happen in the business application, not in economics, but in business, it's very common. Okay. And sometimes you would see this is so convenient. Okay. So there are two special cases that would deliver what we want. Okay. There can be more, but at least this is two commonly cited in the literature. The first one is your utility is contracted. Okay, your wealth is depend on linear in A, but diminishing on B, right? Because this is how you have the concave shape, right? You have to get that one. Okay, and there's no particular meaning, but just saying that okay, your utility can be approximated by a second order Taylor series approximation, right? There's no third order term, right? Because you learn, right? Any nice smooth function can be approximated by any polynomial, right? And you approximate up to second order. Okay, if you think this is okay, then you will take contracting. That's fine, right? That's what you have, right? And the second one is what we said, the constant absolute risk aversion, right? And this is not sufficient, right? Because this is so convenient, right? So what is lacking here is you to assume that the lottery or the risk follow normal distribution, right? Which is sometimes it's okay, right? Because by by central limit theorem, right? That if the risk is behave nicely, then it's normal. Of course, we know this is not the case, right? But that is something we can assume, right? If you're happy to assume that, then this classical mean variance approach will apply. Okay? The proof is very simple, but you can check the one-page proof. It's saying that if your utility like this, you only care about the mean and variance. Okay? So no matter what lottery looking at, okay, as long as mean variance same, then it's same. I mean, I just try to give you the quick proof because that is very simple, right? If this is your expected utility on W plus L, if you have linear on your wealth, right, and B on this one, right, this is what you have, right? Because expectation can take to inside, and then you just open the square and you cancel it out, and then only thing you can see is this only mean and variance. Okay, so you give you two lottery, have the same mean and same variance, right? They're identical. So I don't care about mean and variance, right? So that means that is very simple, right? I don't need to worry about the kurtosis. I don't need to worry about skewness here, right? And of course, probably some of you would know, you do the finance literature, right? The recent 5 years, they figure out that, I mean, people value kurtosis and skewness, right? Especially skewness, right? But anyway, there's a classical model we're talking about. And this is also very commonly in the finance literature. Okay. Operation literature is like people have this exponent utility. And if the uncertainty comes in L, then what you care about is the mean and variance utility just based on this particular guy, right? If mu plus 1 over half R sigma square, right? So you will often see in the model, they would just say, okay, because W is a constant given. So basically they would do is the objective function is to maximize this mu minus a parameter times the standard deviation, right? Usually what you see in the literature is maybe A minus B sigma square, right? Of course, now we tell you that what B is half of the risk aversion there, right? And of course, this is the parameter that is how risk averse you are, right? And that is the foundation, okay? The proof is rather simple, but I just will briefly go over it, right? Very quickly. So if normal is like this form, right? You can put it inside here, okay? And just with some trick, because of E and E, then you can simplify, right? Because your utility is exponential and normal turn out to be exponential. So you can add up this, right? And some simple algebra, not so simple, but I mean, it shouldn't be very difficult for a PhD student. But anyway, no matter how well you do at the end, you can simplify to this form, which is utility depends on only this guy, right? Only this part matters. Okay, so we often see this is the form, right? Tell you that you maximize your mean minus some fraction of the variance. Okay, this is rather normal, right? That's why you can see table. Okay, assume the guy is a mean variance optimizer. This is how we start. Okay, I hope this gives you a foundation why this is true, because it's so often they just start right away. Assume this is a mean variance optimizer, right? That's the reason. Okay, is as long as you assume the constant risk absolute aversion and assume the uncertainty derived from normal or the bell curve, then you're happy. Okay. Of course, the question is, if not bell curve, then what you're going to do? Usually you don't have there's not a mean variance optimizer, right? You have to focus on other things as well, not just the mean and variance. Okay. And again, there's some application. Very quickly, I think this is nothing very deep here. I don't want to spend too much time on that. If your two stocks have same mean and same variance, but they have still covariance, right? If you put all your money in one another, your variance is the same, right? But if you split, the variance is reduced, right? Because there's still covariance. Okay. So that means that why you talk about this? Everyone knows it, right? You don't put all the basket, but don't put all eggs in the same basket, right? And why we will talk about this? The reason is being that now we're talking about this is the mean the same, right? The variance are different, right? It's a mean preference spread. That means it's second order stochastic dominance. That means that regardless of your risk preference, as long as you're risk averse, no matter how risk averse you are, you want to diversify, no matter what. Okay, so calculating a diversified portfolio doesn't have to ask whether how risk averse you are, right? So that means unless you're risk loving, just put everything in the same basket, then you're done, right? But the diversification doesn't rely on the fact that how risk averse you are, right? It doesn't say, okay, you are that risk averse, you want to do that, right? That means that there would be an efficient portfolio, right? Or efficient frontier, right? There. It is the first thing. And okay. And the second one is called contingent commodity. Okay. You can say this is the model, is how you price uncertainty. Okay. And it's very simple, but maybe go about that because it's you often see that in the literature as well. Okay. So it's very simple. The world only have good or bad. Okay. And good has probably pi and bad is 1 minus pi. And you start with initial wealth W. And it's either, if you're good say you WG and you're bad you WB. Okay. Okay. And this is the so there's a different good. Okay. Maybe a not very good notation. But anyway, I think I copy from somewhere the notation. But anyway, this is the good, should be XG is better. Anyway, good in the good time, good in the bad time. Okay. And the price of the good in the good time is called PG. The price of good in the bad time is PB. Okay. And utility depends on expected utility, right? So it's just like you in a good time, this is the good, and a bad time, this is what you have. Okay. And your budget constraint is how much initially W you have. Okay. And assuming interior solution, okay, your marginal substitution should be same as the price ratio. Okay. And now assume the market is competitive. Okay. The price represent the odd ratio. Okay, it's competitive market. So if you try to trade, you should break even. Okay. In that case, okay, you put pi over pi here. It must imply that, okay, you would be having a 1 for the marginal utility. Okay. So it means that if there's such market, okay, we will try to make sure that no matter what kind of outcome, okay, you get the same wealth. Okay, so that is the how people will want. Okay, if there exists a market that do the trading, okay, if there exists, this will hold. All right, but of course, this market doesn't always exist. But if this exists, then it means that people will try to make sure that they diversify the risk, right? No matter what you do, right, then it always the same. Okay, so make sure that certainty line, right? That explains why in the marriage market there's someone called backup, B.B.A, right? So if this fails, then there's another one to line up to come, right? So always make sure in good time you have someone to marry, and if this doesn't work, there's someone to get married, right? So the other one is talking about insurance, right? And the question is, at the end of the day, it's trying to tell you, at the end, right, what people would do the same as before. I'm not going to go over, but at the end of the day, is everyone would buy full insurance, okay, to cover his uncertainty, okay. And if it's fair, then he will buy full amount, okay. So the question is very simple. You have the wealth, some wealth. You have some probability you have loss because of sickness or accident, okay. And the insurance companies is charging the premium P for every coverage. So that means that individual is choosing the Q level from 0 to I. Right? And then if things happen, he will lose L. Okay. But because he have the coverage Q, he get back Q, but he have to pay for the coverage cost PQ. Because every level of coverage is pay P. And if there's no loss happen, you just pay the premium, right? Because there's no L and Q. Okay. And individual just choose the coverage level. And we're going to show you that as long as the P is fair, you buy Q up to you buy the corner solution I. Okay. There's no interior solution when the insurance company is fair. So you would buy to make sure that you have no risk. Okay. So if you do this general form, and what you're going to do is to take the FOC, which is not surprising, right? This is the gain of buying insurance, right? This is when this is the bad time, right? Things happen, and this is the cost of doing it, right? Because in the bad time, then you buy more coverage, you lose some more money, right? So you rewriting terms, okay? This is what we got. Okay, this is very similar to what we have, right? And if you have actuarial fair, means that the insurance company making zero profit. Okay, so insurance company pay out, and what they earn is the same. Then at the end, it means that the insurance premium is same as probability things would happen. Okay, and it turn out that the decision maker to make sure that when things happen and don't happen, the magnitude is the same, right? That means that you take the same in the same value, right? So that means that you buy full insurance. Okay. So of course you can see here is if you're risk averse, you would buy as much insurance as possible. If there's an implication. But you do notice that this is not possible in the real world because the insurance company is not fair. So that's why we don't buy that much. And insurance company is not fair. It's not because of insurance company are greedy. Insurance company usually is actually very competitive, right? And especially for the liability insurance, not the life insurance. Life insurance is not that competitive, but for car insurance, fire insurance, they're very competitive. And the reason probably you know why this doesn't work because of Lemon's market, adverse selection problem. So that makes that the insurance company cannot offer fair insurance policy, because if that's the case, that will attract all the bad risk, right? But we'll talk about that in contract theory when we have time. But it means that we will try to buy as much as possible. Okay, if everything is perfect. Okay. So a final remark on this is we do not talk about one very important model in the literature, which you increasingly see more common, but this is also not in standard textbook anyway, at least not in the introductory advanced level micro. Okay, usually if you look at the micro sequence 2, they will talk about this, or 3 or 4, but not in the first year PhD class. It's about prospect theory. Okay, so here we focus on the final wealth, right? Your utility derived from the ultimate money you got. And prospect theory said you are not deriving utility from your wealth, but rather the main thing you will focus on is win or loss. And then you treat win or loss are different. Okay, that's called the your utility function is concave in gain and convex in loss. Okay, it's somewhat like this, right? If you like, right, it is something like this. Your wealth, okay, your utility is something like this: concave in gain and convex in loss. Okay, you always move the reference point to your gain and loss. This is 0 to be exact, right? And as I said, you also have probability weighting, okay? Which means that you don't weigh probability evenly, right? And so what I meant is, you can imagine one way to think about this is, instead of PI UXI, right? This is expected utility, right? And probability weighting means you have something like this: V of PI, right? U of XI. Okay, it's not linear. And V is a function from 0 to 1 to 0 to 1, right? So 0 to 1, probably P, right? The V, right? And the classical one is a 45-degree line, right? This is the classical assumption, the 45-degree line. And prospect theory would set it's something like, I forgot, this is like that. I remember something like that. Something like that. If I remember, no. I remember something like that. I don't recall. You can check the test. Something like, I think it's something like that. If I remember correct, I forget. Sorry. I think it's something like that. The reason is being that people tend to underestimate the unlikely event. So if something is, oh no, this should be the one. Okay, I think it's like this. Yeah, I think this is right. Okay, so that's why people buy lottery, because although it's very small, you would tend to evaluate more than it should be. So that's why people would want to do that. And this also explains why people were willing to say when it's very close to, it's a bit close to go back to 1, but when it is something like that, right? But it's just trying to explain when it's very likely, but almost so likely, but you still 100% sure, but you still want to pay a little bit amount to make sure things would happen. You extra precaution, right? People are very sensitive to that, but this is the idea. And as I also hinted, this actually means a lot of things, but some sense that skewness is important. Whether you would want to look for a super growth stock like Tesla or Google, right? Or now it's a AI company, right? So they want to look at those. Okay, I hope I give you the overall of the uncertainty. I mean, there are many things you can do, but I'm not going to spend time on that. If you have time, we can go back to talk about prospect view or other thing. But this is what I have for today. And we will be I will be releasing the second assignment later this week, probably before the hiking holiday, so that if you have nothing to do on the top of the hill, then you can solve some solution there. You can look at the concave shape of the hill or convex shape of the hill to give you some idea. But after that, we'll go to the game theory. That will be the rest of the fall. If you have time, we talk about some concept theory or other application. But I think these are very useful things. So I hope at least up to this point, you can already figure out how to do your project, because you should be start working on your projects, which I said you are allowed to do many other things, right? You can write a literature review, you can look at some model that you have been doing, or you can write your own paper. Okay, start to do something. In the case that you really unsure to do, you should schedule an appointment with me, talk to me, and see whether it's okay or not. But the easiest thing is look at the literature in your field, look at some of the model, and you write some comment on those, right? Or that would be the easiest. Okay, you can collect some papers, some recent model, and you can try to understand what's going on there. That would be the easiest thing to do. Of course, the most rewarding is to write paper, right? I mean, look at what assumption there, right? That would be much more fun. But I know all of you are very busy, so I don't insist on writing papers, but you can do whatever you like, just open-ended assignment, okay? So, or you read some frontier paper, then you can try to tell me what's going on. That will be fine. And remember, I limit to no more than 15 pages, okay? So double space, so don't write a lot, because time for you is very important. Time for me is always important, right? I don't want to read too many, right? So just make your life easier, make my life easier, write very concisely, okay? So I will see you next week. If any question, just feel free to email me. Yeah, happy for the festival. Have fun.